Ambient air flows over a heated slab having flat top surface at y is equal to 0. The local temperature profile in Kelvin within the thermal boundary layer is given by T as a function of y is equal to 300 plus 200 e to the power of minus 5y, where y is the distance measured from the slab surface in meter. If the thermal conductivity of air is 1 watt per meter Kelvin and that of the slab is 100 watt per meter Kelvin, then the magnitude of temperature gradient dt by dy, that is temperature gradient in y direction, within the slab at y is equal to 0 is dash. So we need to find the temperature gradient in Kelvin per meter when y is equal to 0, and that too rounded off to the nearest integer. To calculate the magnitude of temperature gradient, let's draw the thermal boundary layer over the slab. Let's say this is the thermal gradient which is present because of the heat transfer between the hot plate and the free stream fluid. This profile of temperature gradient is given in the problem that it's a function of y, that is equal to 300 plus 200 e to the power of negative 5y. Let's say this surface here, it is at y is equal to 0. So let me write here, this is y is equal to 0, that is the top of the surface, and the thermal boundary layer that is in contact with the slab is this layer. We can assume that it's a very thin layer over here. Okay, so let's say this is the layer in contact with the slab. Now the heat flux that is leaving this slab must be equal to the heat flux gained by the air, and that will be same in the top layer, right? In this layer it will be the same. So let's write the heat flux by the slab. So K slab dt by dy at y is equal to 0. Okay, this is for a slab. So let's write here slab, and this should be equal to the heat gained in this first layer. So heat gained in this first layer will be equal to this quantity. So let's write negative K air, this is the first layer of air, dt by dy at y is equal to 0 of air, right? Let's say this is equation number first. Now the temperature gradient is already given in this problem, and that is thermal conductivity of the air is also given, and which is equal to, let's write here, K air is given 1 watt per meter Kelvin, right? And this K slab is also given. So let's write here K slab is equal to 100 watt per meter Kelvin. That means the thermal conductivity of air and the slab both is given. Now in this first equation, in the right hand side, dt by dy, that means the variation of temperature in y direction of air, can be found out by using this equation, that is the temperature profile given. So if we differentiate it with respect to y, we will obtain this term. So let's do it here itself. Let's write dt by dy is equal to, so the first term will be 0 and the derivative of second term will be constant, will keep here, e to the power of minus 5. So minus 5 will come here, e to the power of negative 5y, or we can also write it as minus 1000 e to the power of minus 5y. Okay, let's say this be equation number 2. Now we have all the information to calculate the temperature gradient of this slab, right? So let's substitute in this equation number 1. Let's write this as equation number 3. Okay, so substituting equation number 2 and equation number 3 in equation number 1. Okay, what we will get from here, let's write. Now from here we can calculate dt by dy for slab. Okay, so let's write here dt by dy at y is equal to 0 of slab, and this should be equal to thermal conductivity of air and this value is given to us is 1, right? So let's write 1 divided by K slab, that is 100, multiplied by dt by dy at y is equal to 0, right? So we have got dt by dy. So if we put y is equal to 0 here, we have negative 1000. So let's write here minus 1000, and this is also negative. Okay, so we get the value of temperature gradient in y direction for slab as negative 10 Kelvin per meter, and only if we need the magnitude, so we can write dt by dy for y is equal to 0 slab, and if we are taking only magnitude, so we can write this as 10 Kelvin per meter. Now let's go back to the problem and fill in the blank. The magnitude of temperature gradient dt by dy, so we need to calculate the magnitude only at y is equal to 0 is 10 Kelvin per meter. To get more information on this topic, you can refer to the NPTEL course, lecture number 19, Integral Method for Laminar External Thermal Boundary Layer over Isothermal Surface, on the course Convective Heat Transfer by Dr. Arvind Pattamata and Professor Ajit K. Kolar of the Department of Mechanical Engineering at IIT Madras.